Hello, how are you? Ugh, here we are again. I can't believe you're back for more. That's pretty impressive that you're that dedicated to this class. This is pretty dry material, but now we're taking a little departure now from polynomials. I mean, although we've been studying polynomials and how to graph them and all that stuff, now we're talking about, in this section, 3.5, rational functions and their graphs. Although rational functions, they are related to polynomials because, as we'll kind of see below, we'll write it, but just so we see a rational function, what the hell is that? If you've never seen that before, it's a function that looks like, let's see, f of x equals, I think they usually write it as p of x over q of x. So it's pretty much, it's a fraction where your numerator and your denominator are polynomials. So it's kind of like, now we're making it even more interesting. Instead of just studying one polynomial, we're going to study a fraction where the numerator is a polynomial and the denominator is a polynomial. So and then, okay, first, in this little box they're talking about kind of where that's useful. Sometimes in real life, some functions or some real life quantities can be modeled by rational functions. So it says decreasing costs with increased production. So that kind of makes sense, you know, in real life, you know, that if there's a manufacturer that makes only 5 items or something, you're gonna have to charge a lot to make it worth it, right? Because that was a lot of work to make those 5 items. But if instead you made 5,000 items, well, you probably get some kind of deal, and you probably have some kind of manufacturing facility, and I don't know, yeah, you get a deal on the materials and stuff, so you could probably sell your items for less the more you make, you know, that kind of thing. Anyway, what does it say? In a simple business model, the cost, we'll call it c of x, that's a function, to produce x units of a product is the sum of the fixed and variable costs. Okay. So I guess fixed cost is like, you know, the facility you're manufacturing at, that cost of that was already fixed. The variable cost might be materials, you know, sometimes materials prices go up and down and other things like that. But that can be expressed in the form c of x. So they're getting specific now. Let's say their fixed costs are 500,000. That's how much it costs them to make any amount of items, plus 400 times x. So x is the number of items. That must mean that the fixed or the variable cost is 400 times every item they make. In this model, the cost increases by 400 for each additional unit. If we divide the cost c of x by x, the number of units produced, then we obtain the function c of x bar, because it's got a little bar over it. I don't know if you can see that very well. Which represents the average cost of each item. By studying the rational function c of x bar, we will, let's see what, see that the average cost per item decreases for each additional unit. So yeah, like we said, that kind of makes sense instinctually if you know anything about business or you've heard anything about business. Yeah, kind of makes sense. All right. But first things first, we're going to do a little review. Because remember, finding the domain is review. We already know how to define, to find the domain of anything. If it's been a while, remember, the domain of a function, it doesn't matter what kind of function, all you're really looking for is there a root in it? Because if there's any kind of even root, you have to worry about imaginary numbers. And if there's no root, like we see in parts 1 and B, or 1a and 1b here, then you're looking for a denominator. But we do have denominators here. You just want to make sure now that the denominator can't be 0. So that's why we'd find the domain of these guys. We're going to set the denominator equal to 0 and solve for x. Those will be the values we don't want in our domain. So this first denominator, x squared minus 25, if I set that equal to 0, I guess I could get x by itself and all that stuff. I'm going to add 25 to the other side. So x squared equals 25. If I square root both sides, just definitely don't forget, when you square root both sides, you have to put plus or minus. If I put a plus or minus there, then I have plus or minus 5. That means the domain I want is the set of all x such that x is a real number, because x can be anything it wants as long as it's not imaginary. Is a real number, and x cannot be 5 and x cannot be negative 5. Because those are the values we found. Those will be the values that'll make that denominator undefined, which is bad. But notice if we try to do that for this guy, if I set that denominator x, now it's x squared plus 25. If I set him equal to 0, now I'm solving it by subtracting 25 instead of adding. And now I'll square root both sides. -25. So I have to put plus or minus Notice it's negative 25 inside. Those are imaginary values. So when when you're trying to solve an equation and your solutions are imaginary, that means there's no solution. Well, unless you care about imaginary solutions. But in this case, we're only talking about real numbers. Yeah, when we talk about domain, we're only talking about real numbers. No solution, that means that the domain can be anything it wants. Because what we just did when we solved that equation was to find out the bad values. What are all the values that would be bad for x to be? Since there are none, we found no solution. There are no bad values for x. That means x can be whatever the hell it wants. So the domain is the set of all x such that x is a real number. Not so bad. So I just wanted to go over one like that so you've seen it before. So to find the domain of a rational function, you set the denominator equal to 0. If you get solutions, or one solution, multiple solutions, you just exclude those from your domain. If you get no solutions because you get imaginary numbers, then the domain is all real numbers, like we've seen before in some functions. Alright, the next objective is to use this arrow notation, which this will be very useful in calculus. I know I say that a lot. You won't see this too much in the near future, but in calculus you'll see this over and over, and it's kind of confusing unless you've seen it before, so this should help. Used in calculus. Yeah. Okay, so the first notation that we're going to kind of look at is it says the notation x arrow a with a little plus sign. It means that x approaches the value of a from the right, and the notation x arrow a negative means x approaches a from the left. So it's kind of a weird idea, you know, but if you kind of picture it, it sort of makes sense. Let's see, here's x, here's y. And then a, let's say a is just some x value, like say here. So notice, you know, if you look at the x-axis, if you go to the right on the x-axis, that's all the positive numbers, right? If you go to the right on the x-axis, that's all the negative numbers. Or you can think of it as this is the positive infinity direction, this is the negative infinity direction. So I guess if I'm approaching the x value of a from the right, I'm coming from the positive direction, which is why we say this. X approaches a from the right side. But if I'm approaching a from the left side, I'm approaching it from the negative direction because I'm coming from the negative numbers. So it's kind of the idea behind this notation. So, okay, what does this say? True or false? They just want to make sure we understand this notation. The notation x approaches a, if you can't see that, that's supposed to be a little plus. It means that the values of x are increasing without bound. That would be a false. False. When they say the values of x are increasing without bound, that means x is getting larger and larger and larger. Yeah, x going to a plus does not mean x is getting larger and larger forever, which basically is what increasing without bound means. It means that x approaches a from the right, or from the positive numbers, I guess. Yeah, sorry, this is hard to read, huh? Forever. Okay. And then this other notation, this one's a little more complicated. Let's try to decode this. The notation f of x goes to b as x goes to a means that when x approaches the x value of a, the function's y value, or f of x values, approach the y value of b. Okay. This is clearly more complicated because now they're involving y values, or f of x values. So let's say this, let me kind of draw the scenario so we kind of get what's going on. Here's the x-axis, here's the y-axis. Now they're involving some kind of function, so let me draw some kind of cute little function here. Let's say, we gotta do this guy, okay. So let's say it goes, woo, I don't know. It's kind of a cubic shape. Say there's f of x, his graph. And then we'll just designate kind of a random value of x. So let's say here's, I don't know, here's a. Okay, then f of x goes to b, then that means, the way they're phrasing it, they want b to be the y value associated with a. So here's a point a comma b. Alright, so that's kind of what the basic setup, but they're saying, okay, the notation f of x goes to b as x goes to a means that when x approaches the x value a, okay, so let's say, I'm going to use a different color. Let's say, imagine me trying to like walk along this function. I'm going, let's say from the left side, I'm going, see these little green dots? kind of on the bottom of the function. I'm going, I'm approaching A. I'm trying to get closer to A. So what y value am I going towards? I'm going towards a B. The B is the y value. Same thing if I was coming from the right. I'm going da-da-da-da. I'm trying to go towards an x value of A. Well, I'm trying to just go to the x value of A, but I'm unintentionally going to a y value of B. That's kind of what they're saying here. Yeah, when x approaches the x value of A, the function's y values approach the value of B. Alright, so let's see what they say. True or false? If f of x goes to 0 as x goes to infinity. Let me picture that before I even read any more. Let's see. Okay, let's see. F of x goes to 0 as x goes to... Well, x going to infinity means you're going this direction, because infinity is the positive direction to the right, and then negative infinity would be to the left. If f of x goes to 0, let's see, and f of x, remember, is the y value. So y is going towards 0 as x goes to infinity. That means that if... I don't know what your function looks like, but maybe it's going like da-da-da-da, and then it goes... It's going towards a y value of 0, so it's kind of narrowing in on the x-axis like that. Because that means as you're going towards the right... Yeah, that's what this means here. Let's see. Going to the right. That's because x going to infinity means to the right. Then y goes to 0. Yeah, that's true, because your y values are going down towards the x-axis, and the x-axis is a y value of 0. Then the graph of f of x approaches the x-axis to the right. I'd say yes, or true. That's exactly what that means. We'll never see this notation again. I mean, maybe once or twice in passing, you know, we'll talk about it a little bit, but this was more just so if you've seen it, so in calculus it'll be easier. That's all. It's kind of confusing. I think that's why they introduce it now. I know when I took calculus, I had never seen that arrow notation before, and I had a really hard time. So I wish I would have been exposed to it a little earlier. Even if I didn't get it all the way, I think it would have made it easier. So our next objective is to solve polynomial equations. Okay, let's see. And then they kind of give us a hint here. They say, note, to determine the vertical asymptotes of a rational function. Okay, and this is, like we said earlier in this section, this is kind of what rational functions look like, where p of x and q of x are polynomials. Reduce f of x to its lowest form, then set the denominator equal to 0 and solve for x. That'll be the vertical asymptotes. Okay, so maybe even before we do that, we should talk about asymptotes. I don't know if we've talked about that yet. You might have seen it if you took an algebra class before this, but if not, it's okay. Asymptotes are lines that the function's graph approaches. And we actually have a graph that we've memorized that has one, but we didn't even know it. It actually has two. The graph of y equals 1 over x. That's one of the graphs that we kind of memorized at this point, hopefully. Let's see. He looks like this. He kind of curls up in the top right corner and then the bottom left corner. If you haven't memorized this graph by now, then here he is. He looks like this. But actually, since it's approaching, notice as it goes upward, it's approaching the y-axis, so that means that the y-axis is the vertical asymptote, because the graph is getting closer and closer to it. So let's see, x equals 0, which is the y-axis, is a vertical asymptote of this y equals 1 over x. And actually, y equals 1 over x is a rational function, 1 over x. It's just like the simplest one you could possibly think of. And there actually is a horizontal asymptote too, but we haven't really talked about that yet. That's kind of the idea behind it. But if you want to find it mathematically, you know, instead of finding this guy's graph, because we don't know how to graph these yet, this complicated guy, if you want to know where his vertical asymptote is without looking at the graph, you can do it mathematically by the steps that are outlined in this box. It says first you got to get it in lowest terms, so that means that I have to factor numerator and denominator as needed. Factor. Okay, well the numerator doesn't factor. You know, it's as simple as it gets, x minus 1, but the denominator actually is a difference of squares. I can write it as x minus 1, x plus 1. And now the x minus 1's cancel just to leave 1 over x plus 1. So the function that they gave me was actually not simplified all the way. I can write it as 1 over x plus 1. Okay, now that we've written it in lowest terms or reduced it, Now, as it says here, we're going to set the denominator equal to 0 and solve for x. And whatever we get, that'll be where the vertical asymptote is. So if I subtract 1 from both sides, it looks like x equals -1 is the vertical asymptote. So not that you have to graph it, but just in case you're kind of curious about it. X equals -1 is a vertical line, obviously. It goes do 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 do. So I'm not really sure what the graph of this g of x looks like, but I know that it's going to approach that line for sure, either from the right or from the left or both. So kind of interesting. And then we'll find the vertical asymptotes of this next guy. And this one actually is nice because they've actually what's it called? They've factored it for us, so actually I can just start putting it in lowest terms by canceling those x's. So it's 1 over x plus 4. I can find the vertical asymptote, or asymptotes. Sometimes there's more than one. It just depends how many solutions you get when you do this part right here. I'm going to subtract 4. It looks like x equals -4 is where the vertical asymptote is. And again, that time we only got one vertical asymptote, but sometimes there are more than one. And the next objective is how to find horizontal asymptotes, which is more complicated. So this one is going to be a lot to remember. Ugh. This one might be one worth writing down for sure, like on the note card or something like that. So the horizontal asymptotes, it all depends on whether the degree of the numerator or the denominator is bigger. So if you have a polynomial on top that has a higher degree than the polynomial on the bottom, you're going to have a certain kind of horizontal asymptote. If they have the same degree, it's a different kind. You know, if the bottom has a higher degree, then it's a different kind. That's what you kind of have to do. So it says, okay, to find the horizontal asymptotes, compare the degree of the numerator, we'll call it m, and then to the degree of the denominator, we'll call it n. If m is less than n, then y equals 0 is a horizontal asymptote. It's just, that's what it is. You don't have to do any kind of math. If m is greater than n, so the degree of the numerator is bigger than the degree of the denominator, then there's no horizontal asymptote. So some functions have none. If they're equal, then you divide the leading coefficients, and that'll be your asymptote. It'll be y equals m over n, like that. So I'm going to kind of number those. Let me see. That way I can kind of keep track of which situation I'm in when I do the examples. So this example 4a says find the horizontal asymptotes of this rational function. So m in this case, the degree of the numerator is 2 because that's the highest power I see there. N is actually also 2 because that's the degree of the denominator. So I'm in situation number 2 from that box. Oops, situation... Situation 2. Oh no, sorry, 3. Son of a gun. Because m is equal to n. So that means it says that my horizontal asymptote should be the result of me dividing the leading coefficients. Oh wait, that's not it. Sorry. It's the leading coefficient on the top divided by the leading coefficient on the bottom. The numerator is just 9x squared, so 9 would be the leading coefficient. The denominator's leading term is 3x squared, so it should be 3. And if that fraction didn't reduce, then I'd just leave it as is, but that actually does reduce to 3. So y equals 3 is the horizontal line that makes up the horizontal asymptote here. And the next one, now it says, find the horizontal asymptotes if any. Okay. So this is a similar thing. I have to figure out what's the degree of the numerator. It looks like the degree of the numerator is 1 because that's the highest power I see. But actually the same in the denominator. So I'm in situation number 3. Where I have to say that the horizontal asymptote is y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So the numerator's leading coefficient is -2, the denominator is 3, and that's it. That doesn't reduce, so I'll just leave it like that, -2/3. Y equals -2/3, that's the horizontal line that the graph approaches. Alright, let's try that with this next guy. 4c here. Find the horizontal asymptotes if any. Alright, the numerator has degree 3, the denominator has degree 2. So which situation is that? Let's see. So obviously there m is greater than n. Which one was that? That was situation number 2. M is greater than n. number 2. What does it say to do there? There's no horizontal asymptote. Okay, no horizontal asymptote. Alright. Okay, and the very last one in this objective says, here's the function, now find the horizontal asymptote. The degree of the numerator is 1, the degree of the denominator is 2. So that means we're in a situation where m is less than n. And I think that's situation 1. Situation 1. Is that right? Let me see. M is greater. Yeah, okay. So in that case it says then y equals 0 is a horizontal asymptote. So no need to do any work, that's just the way it is. When the degree of the numerator is smaller than the degree of the denominator, just automatically y equals 0 is it. No need to do any work. And let's see, now we're going to use transformations to graph rational functions. Okay. So because remember we just talked about the graph of this guy, f of x equals 1 over x. So that guy, maybe we'll kind of bring it down here so we have it sitting next to us. It looks like kind of two pieces. The top right piece hugs the x and y axes up there, and then the bottom left piece kind of does the same thing down in this corner. But we're going to use transformations to graph this guy. So we have to kind of dig deep back into chapter 2 where we have to figure out that 2 down there, does that move it left or right or up or down? Well, this plus 2 actually moves it, let's see, left 2. I have to think about that. Left 2 units. And then this negative 1 moves it down 1 unit. 1 unit. I think especially when you graph rational functions like this, I think what helps is as you're moving, using transformations and stuff, it helps to think about where the asymptotes move. So y equals 1 over x, the original guy, he has a vertical asymptote right on the y-axis and a horizontal asymptote right on the x-axis. So I would move the asymptotes. Move asymptotes. So I'm supposed to move them left 2 units. Okay, that would mean that the vertical asymptote moves from right on the y-axis to the left 2 units. So that guy. And I guess if you think about a horizontal asymptote, what if you move a horizontal line to the left? It doesn't change it at all, so that didn't worry. I didn't worry about that. But a horizontal asymptote, if you move it down 1 unit, that would change it. Now all of a sudden he's 1 unit lower than he was. He was on the x-axis, now he's 1 lower. Okay, but now that you know where the asymptotes move, now you can just graph kind of the same graph as what it was before. It looks like this. It's just now instead of approaching the x and y axes, now it approaches these new asymptotes that moved left and down. Okay, now we'll try to do the same thing for 5b, but notice this guy, he kind of doesn't look like the last one. The last one kind of had a nice look. It looked a lot like f of x equals 1 over x. It's just that it had the extra number next to x and a negative 1 at the end. This one, though, it kind of looks very complicated. So this I wanted to throw in because I could see them trying to trick us with this. I would use, what we need to do here, yeah, is use long division to make this look more like what we saw in 4a, you know? Is that 4a? Oh, sorry, 5a. 5a. So we're going to divide, because really a fraction you can think of as a division problem. X minus 2 in the denominator, 3x minus 3 in the numerator. That really means x minus 2 divided into 3x minus 3. I'll do long division. Let's see, it's going to be x divided into 3x makes 3. I'm supposed to multiply that by each of the guys outside. 3x minus 6. Okay, and then I'm supposed to subtract, but remember, you can't forget to distribute the minus sign. That's going to make the 3x negative and the 6 positive, which leaves you as a remainder of 3. So the answer is the quotient. Okay, the quotient 3 plus, let's see, and we're supposed to write our answer as the remainder, which was also 3. Oh, son of a gun. There we go. Over the divisor, which was x minus 2. Alright, so that's how we want to write it, and that's going to make it easier. So our function, what do we call it, f of x or g of x? F of x. Can be written as, okay, 3 plus 3 over x minus 2. Okay, and that looks a lot more like the previous one, 5a, except you know what? I'm going to switch these two terms. I'm going to write 3 over x minus 2 and then plus 3. That looks a lot more like what we're used to. So this 2 is going to move it to the right 2 units. This 3 is going to move it up 3 units. And this 3, this is supposed to be like your vertical stretch or shrink. It's supposed to stretch vertically 3 times. But I think, to me, honestly, that's not as important, because if you look at the graph, if you look at the graph of 1 over x, this guy, if I were to stretch that vertically, I don't even know if I can tell, because it's kind of a weird graph, because it's like approaching the x-axis, it's approaching the y-axis. I know, it's kind of tricky, so that part, it's kind of hard to show. But the main thing is you definitely want to show that you move things to the right 2 units and up 3 units. So like we said, if I move this to the right 2 units, that's not really going to affect the horizontal asymptote, because if you take a horizontal line and move it to the right, nothing happens. But the vertical asymptote that was on the y-axis, if I move it to the right 2 units, now it's to the right on x equals 2. And then if I take the horizontal asymptote, which was on the x-axis, and I move it up 3 units, now it's going to all of a sudden be, at y equals 3, like that. So the asymptotes moved, and then, I don't know, it's kind of hard to show the stretch or the shrink, so I'm just going to say whatever. It's tucked up in the top right corner and the bottom left corner. But again, now you're not trying to approach the x and y axis, because it's almost like they moved, they moved right and up. So those are how you graph the type of rational function that can look a lot like 1 over x, because we know what 1 over x looks like. So anything that kind of has that form, we can just use transformations to graph it. But the next objective kind of tells you what to do. How do you graph a rational function when it looks nothing like 1 over x? It's not that simple. It's really complicated, so we have to really think about it. It's kind of like, yeah, at this point we kind of have to put everything together that we've learned in one long problem. Ugh. Okay, here are our steps. Oh, I'm going to try to follow these as best I can. Did I leave myself enough room? I don't know. We'll see. First thing is to reduce f of x to lowest terms if necessary. So I'm just going to go through the steps. Step 1. It's already done because this guy doesn't factor. The numerator doesn't factor, the denominator doesn't factor, so I don't have to worry about that. Then we'll determine if the function has any symmetry. Let's see. And that's where, remember, you replace x with negative x. X with negative x. Okay, f of negative x is negative x to the 4th, negative x squared plus 2. Well, since all the powers on x are even, they're just going to swallow up those negatives as if they weren't there. And if you remember, if you put a negative in for x, and you get the same as the original function, that means this is an even function or it has y-axis symmetry. So that might help us, because in the coming steps that we're going to do, steps 3 through 8, we might kind of get hints as to what the graph looks like on one side of the x-axis or the other. So we might have a really good idea of what's happening on the right of the x-axis, but not the left. But now that we know that it has symmetry, we just copy the right side on the left side and vice versa. That's, I guess, the beauty of symmetry. Step 3 says we're going to find the y-intercept, which is f of 0. So this should kind of give us an idea of sort of what the graph looks like around the origin or around the x-axis, or sorry, the y-axis. If I replace x with 0, I'm going to get 0 over 0 plus 2, which is 0. So it looks like it goes right through the origin, because we put x equals 0 and then we got y equals 0. Step 4, okay, find any x-intercepts, if any, by setting the numerator equal to 0. The numerator is, what was it? I already forgot the function. It's x to the 4th. If I set that equal to 0 and I try to solve for x, I would take a 4th root of both sides to get rid of that 4th power. I'm supposed to put a plus or minus, but because I'm getting 0 as an answer, the plus or minus doesn't really matter. But when I think about it, that's actually a point I already knew about. The origin was already a y-intercept. I found that it's also an x-intercept. Big deal. I already knew the graph went through that point. Step 5 says, find any vertical asymptotes as described in objective 3. So remember, vertical asymptotes, let's see. I'm just going to abbreviate it. Vertical asymptotes, you find those by setting your denominator equal to 0 and solving for x. But that guy doesn't factor, so there are no solutions to this guy, because you would get imaginary numbers. Imaginary. So that means no vertical asymptotes. Kind of interesting, huh? Alright, then step 6 says you want to find any horizontal asymptotes as we described in objective 4. Okay. So, okay. Horizontal asymptotes, this was where it depended on the degree. Remember, it's like, if the degree of the numerator is higher than the degree of the denominator, then this and that. Okay, but if it's this and that, blah, blah, blah. Well, if the degree of the numerator is higher than the degree of the denominator, like we saw before, where is it? Blah, 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 like this one, there is no horizontal asymptote. No horizontal asymptote because the degree of the numerator, m, is 4, which is larger than the degree of the denominator, which is 2. So it's kind of weird. This is going to be a weird one. There's no asymptotes at all. No vertical, no horizontal. Let's see. Then we'll plot some points other than the intercepts as needed, and then use the preceding information to graph the function. Okay. Because right now, what do I know? Okay. Step 1, I didn't reduce it. That didn't really help. Step 2 did tell me that it has y-axis symmetry, but I don't think that's going to help right off the bat. That'll help me once I plot all my points and stuff. Step 3 gave me the intercept, so there it is. Step 4 gave me the same intercept. I already knew that. There are no vertical asymptotes. There are no horizontal asymptotes. So all I know right now is that there's a point on the graph at the origin, and the left and the right side are mirror images of each other. So it might be helpful to kind of plot some x values and see what happens. I'll plug some stuff in. X to the 4th, or x squared plus 2. Okay, maybe I'll try, I don't know, 1 and 2 and see how that goes. And then if I still don't feel good, I'll plot more. Let's see, if I put a 1 in for x, what do I get? 1 to the 4th over 1 squared plus 2, that would be 1/3. Right? Yeah, okay, and if I put a 2 in there, 2 to the 4th is what? 16 over 2 squared is 4 plus 2 is 6. That reduces to 8/3. Okay, interesting. Maybe I'll plug a 3 in. Let's see what happens there. If I plug a 3 in, let's see, 3 to the 4th is 81. Holy crap. 3 squared is 9 plus 2 is 11. I'm seeing, what's that guy? 11 goes into 81 7 times with 4 left over. And then 8/3 is 2 and 2/3. So it looks like, it seems like as the x values get larger and go to the right, then your y values are kind of getting bigger too. So the points are 1 and 1/3. Let's see, so he's around there maybe. And then we got 2 and then 2 and 2/3, so he's about here, sort of. And then you got 3, 7 and 4/11. 3, he's about here maybe. So it's kind of going like this, which is kind of weird. And then the right side should look the left side should look the same. So that's kind of a weird, because it's symmetric. So once I know one side, it's symmetric. Y-axis symmetry. Yeah. So it almost looks quadratic. That's kind of a weird one. These are probably one of the toughest things to graph, is these rational guys. Alright. Let's try this next guy. Well, let's try to follow all the steps. I think this one will look more normal than the last one. That was a weird one. The first step was to try to reduce it. Step 1, check because it's already reduced. Because if you try to, I can't forget there's a negative in the front. If I factor the denominator, I don't think either of those factors are going to cancel because there's nothing in the numerator for them to cancel with. So no need to worry about reducing. And then step 2 was to determine if the function has any symmetry. I think it's going to be similar. It's going to have y-axis symmetry. Because imagine putting a negative x in there. That x squared is going to swallow it up like it was never there. And it's going to look just like the original function, which means it has y-axis symmetry. -1 over x squared plus 4. Yeah, same as f of x. That's what we said in a previous section a long time ago. We said if you plug a negative x in and you get the original function back, like nothing changed, then you have y-axis symmetry. So that should help me graph it later. And then Step 3 is find the y-intercept f of 0. So let me try to plug a 0 in and see what happens. The original function looked like -1 over x squared minus 4, but I'm going to put a 0 there. So it's -1 over -4, which is positive 1/4. Oops. So I have a point x equals 0, y equals 1/4. We know 1 point on the graph, that's good. And step 4, that should be an interesting one. Find the x-intercepts, if any, by setting the numerator equal to 0. The numerator is just -1 in this case. So if I try to set that equal to 0 and solve, this has no solution because there's not even an x to solve for, so there must be no x-intercepts. Alright, that was, I feel like a waste of time, huh? And then step 5, I think, was the vertical asymptotes. Yeah. Let's find the vertical asymptotes. And we kind of outlined that in the previous objective. That's where I set the denominator equal to 0 and solve for x. And that guy, you can either factor it or actually just isolate x. You know, I'm going to move the 4 over, and I'll square root both sides. But I can't forget to put a plus or minus when I do that. So plus or minus 2 is where the vertical asymptotes are. I don't think we've seen that yet, huh? There are 2 vertical asymptotes, one at 2 and one at -2. But that shouldn't actually kind of come as too big a surprise, because if I have a vertical asymptote at 2, I have to have one at -2 also, because we said that it has y-axis symmetry. So whatever's going on the right, there better be the same thing going on the left, symmetric to the y-axis. And then step 6 says, find any horizontal asymptotes. Well, in this case, m, the degree of the numerator, is 0, because there is no x term. That's less than the degree of the denominator, which is 2, which means the horizontal asymptote is at y equals 0. That was that weird case where it doesn't matter what's going on, y equals 0 is definitely your horizontal asymptote. And then step 7 was you want to plot some points other than the intercepts as needed. Okay. And you know, sometimes you can actually hold off on that step until you've kind of plotted everything you have on your... I forgot to put a little axis here, but that's okay, whatever. We can make our own, huh? So what do I know so far? I know that it has y-axis symmetry. Okay, that's I'll use that later. It has a point at 0, 1/4. So let me try to plot that guy. 0. No, dang it. 0, 1/4. 0, and then 1/4. Okay, let's say this is 1, and 1/4 is like right here. Okay, and then what? There were no x-intercepts. There were 2 vertical asymptotes. I can plot those. X equals 2 and x equals -2. So at x equals 2, there's a vertical asymptote. And x equals -2, there's another vertical asymptote. Other than that, though, I don't really know what's going on. So, you know what? It might not be a bad idea to plot some values, kind of like in between the asymptotes. Like, okay, I know what's going on at x equals 0 because I have a point there. But let me figure out what's going on. Let's say at x equals 1. I'm kind of curious, where is the graph there? And then x equals... And actually, you know what? I was going to say x equals -1. But we don't have to plot anything for x equals -1 because it's symmetric with respect to the y-axis. So if I know what happens at x equals 1, I only have to plug in values that are close, or sorry, on the right side of the y-axis. I think I'll plug in 1. I would plug in x equals 2, but there's a vertical asymptote there. So there's not really anything going on. Oh crap! And then I forgot to put the freaking horizontal asymptote at y equals 0. Hello, there he is. So like I said, I'm not going to plug in y equals 2 because there's an asymptote there. 3, maybe 3, 4. Let's see how that looks. If I plug in a 1, what was the function again? I already forgot. -1 over x squared minus 4? Yeah. Okay, let's try that. It's -1 over x squared minus 4. Okay, what if x is 1? Then the denominator is 1 squared minus 4, which is -3. So it's -1 over -3, which is positive 1/3. Alright, that's interesting. What if I put a 3 in the denominator? 3 squared is 9. 9 minus 4 is 5, so it's -1/5. What if I put a 4 in there? 4 in the denominator, 4 squared is 16. 16 minus 4 is 12, so I get a negative 1/12. Interesting, okay. And sometimes, you know, you plot a few values and that's still not enough. We'll see. So the first point I found was 1, 1/3. Let's see, he's even a little higher than that other point we have there. And then 3, negative 1/5. So that's just barely below the x-axis. And then 4, negative 1/12. That's even closer to the x-axis. So I think what's going on in this, at least in this bottom right portion, is these 2 points are definitely connected. And it looks like they're going towards the x-axis, which makes sense because there's a horizontal asymptote there. And then since there's a vertical asymptote at 2, it must go down and kind of approach that as well, like this. So at least I kind of know what's going on there. I'm not really sure what's going on in the middle, although I can say, since this thing is symmetric with respect to the y-axis, since there's a point here, there should be a point on the very other side of the y-axis from that guy. So I should be able to put a point here too. That kind of helps. And I think, you know what it looks like when I connect those two guys? And I connect these two guys. It almost looks like a parabola shape because it's going upward. And you know, the graphs of rational functions that cannot cross horizontal asymptotes. So this, all I am able to do at x equals 1 is kind of get closer and closer to that vertical asymptote. Same thing here. So it's kind of like, it looks like a parabola sort of. And then if I'm wondering, okay, well, what's going on this very left side, on the left side of x equals -2? Well, this thing is symmetric with respect to the y-axis. So this portion here, this little part that's hugging the x-axis and the vertical asymptote x equals 2 should be symmetric over here. So I should have a symmetric guy over here looking almost the same. Well, I tried to make it look the same. But if you weren't sure, if you're like, that seems like a leap, I'm not sure, you can always plot more values to make sure that that looks about right, you know? Like the points you put there actually make sense. Okay, and I think this is our very last objective. Let's see, is it? Yeah, okay. Good, because I'm sure you're losing your interest if you had any to begin with. So we're going to now, the last thing is identify slant asymptotes. Yeah, as if this concept weren't complicated enough. There are not only horizontal asymptotes, there are not only vertical asymptotes, but sometimes, not all the time, but sometimes, there are slant asymptotes, which just means it's a line that's diagonal. It's not perfectly horizontal, it's not perfectly vertical. But it says here, if the degree of the numerator is exactly, let's see, greater than a, oh, there's a slant one, yeah. Wow. I should say, if the degree of the numerator, this is wrong, if the degree of the numerator is 1 greater than the degree of the denominator, that's what I should say. So like notice in this example they showed here that the degree of the numerator is 3, the degree of the denominator is 2, which is exactly 1 more than the bottom. That's when you'll have a slant asymptote. Okay, and then you'll find the slant asymptote by doing long division of the denominator into the numerator. The quotient is the equation of the slant asymptote, and you ignore the remainder. Remainder means nothing, it doesn't help us at all. It's just the quotient. So that's pretty much what we're doing here. Notice the degree of the numerator is a 2, the degree of the denominator is a 1, so it kind of fits the bill. The numerator's degree is 1 more than the denominator's. But we're going to find it, like we said, by doing long division of the denominator into the numerator. So this is kind of why we learned or reviewed long division, because we're going to need it here. So let's see. Okay. So do long division. How many times does x go into 2x squared? That would be 2x. We'll multiply him by both guys outside and write it below. 2x squared minus 4x. Now I'll subtract, but I can't forget to distribute that subtraction sign. That'll make this 2x squared a negative and this 4x a positive. These will cancel, but I'll be left with a negative x or a negative 1x when I combine these guys. Because remember, the negative on the 4 is gone. It's now a positive. And I'll bring down the next term. And I'll start my division over again. So how many times does x go into negative x? Or in other words, what would I have to multiply x by to get negative x? I'd have to multiply it by negative 1. Negative 1 times the guys outside would make negative x plus 2. And I'm almost done if I just subtract these guys. Don't forget to distribute. This becomes a plus, this becomes a minus. So the remainder is 5. Not that it mattered. All that work was actually for no reason, because remember they said the quotient is actually your answer. Y equals 2x minus 1 is the slant asymptote. So that's kind of interesting. I mean, they didn't ask us to graph because I think this is getting a little too deep. You'll get really deep into this if you take pre-calculus. You'll get, yeah, this is like a good foundation, you know, but you'll really get into it. But if you care, so the line y equals 2x minus 1 is a slant asymptote. That means if I were to kind of graph this line, looks like this. Okay, this is the asymptote. That means that there's probably some kind of, it probably has a horizontal, no, sorry. Probably has a vertical asymptote. Yeah, it has a vertical asymptote at 2. Like that. So it has a slant asymptote and a vertical asymptote. So the graph probably looks something like, I'm not exactly sure, I didn't put a lot of effort into this. Probably kind of hugs the slant asymptote and the vertical asymptote, and then like this. Something like that is what those guys look like. Not that they asked us to, I'm just saying. This is like a preview of pre-calc. Preview of pre-calc. But right now, as long as we know how to find the slant asymptotes, that's all that matters. Okay, and let's do that on this one as well. We'll do long division like we said last time. Alright, we'll start going. X goes into x squared, x times. Multiply it by the guys outside, x squared minus 3x. And let me distribute the subtraction sign. That would make the x squared a negative, or a minus x squared, but the 3x a positive. That guy with the x above it would make 4x. And I'll bring down the negative 6. Now I'm dividing one more time and I should be done. So this x into this 4x would make a 4. Or in other words, what times x makes 4x? That would have to be a 4. And actually at this point I can stop because all I care about is the quotient. But oh well, it kind of bothers me not to finish it. 4 times x is 4x. 4 times negative 3 is negative 12. And if I subtract, I have to distribute the minus sign, making the 12 a positive. That means the negative 6 and the 12 combined would make a 6. But like we said, it doesn't matter because the quotient is the slant asymptote. Slant asymptote y equals x plus 4. There we go. So the remainder doesn't even matter. So if you messed up at the last step, it doesn't hurt you at all. That's the nice thing. Oh, I feel like this section was bad, but it wasn't as bad as the previous one. I don't know if you agree. Oh, that's a lot. But I think, like I said, I think this class is more like a survey of a lot of crazy math that you're going to see next semester more in depth. So since we're kind of running through this stuff really quickly in this class, I don't think you're really necessarily expected to get it 100%. If you're just kind of grasping onto this stuff, you're probably doing better than the average person. Yeah, this is just more like, if you've seen it now, it'll be easier later. It's okay. I promise that things will get easier in coming chapters. This class is weird, where it kind of starts with the hardest stuff and it ends with the easier stuff. I think pre-calc is kind of like that too, which is weird. It's like, man, if you stuck with it halfway through the class, then things will get better. It's kind of weird. But anyway, thanks for listening. I'll see you in the next video.